last and final topic of digital electronics finally, that is state machines. So we will be covering some finite state machine question, FSM question, into this lecture. Right. So moving on to the first question. So question says that the state transition diagram of the circuit shown. So there is a circuit given to us and they are asking what will the state transition diagram. So now what is the circuit? This is a flip-flop connected and it is given to a mux. So how we can represent the output of mux? Suppose this is Y. This is Y. So how I can write Y? So Y will be equal to, this is your select line, A. So select line, when it is low, it is connected to Q bar, and when it is high, it is connected to Q. So this is your output Y. Now the input to D, in order when we will be finding out the next state, the input is connected to the NAND gate. Now the NAND gate output D is equals to what? D is equals to Q Y bar, because it is a NAND gate. Now how we will be finding out, and D is nothing but next state only, Qn plus 1, that will give us the value of D, next state. So we can easily, when different values of A, we can easily find it out that how the states will be transitioning, right? We just complete it. So that will be Q A bar Q bar plus AQ, and this is complete whole bar. So at two different level, when A is equals to 0, so next state Qn plus 1 will be equal to what? When A equal to 0, so this will become 1 and this will be Q bar plus, and this will be 0. So this. So Q into Q bar, that will be Q into Q bar, that will be equal to 0. So 0 bar, that will be equal to 1. 0 bar will be equal to 1. And next, at A is equals to 1, at A equal to 1, next state will be equal to, so A equal to 1, this will be not there. So Q plus Q into Q, and that will be whole bar. So Q into Q will be Q, and Q bar is be there. So we now see that at A is equals to 0, the output, no matter at what state it is present, the output will be always going to Q is equals to 1 state. And at when A is equals to 1, the output will toggle, right? Because the output, the next state is Q bar. So at A is equals to 0, next state is going to be 1, no matter what. Next state is going to be 1, and at A is equals to 1, next state is going to be toggling. Next state is going to be toggling. So from these 2 points only we can conclude the FSM. Now first FSM, if you see, at Q1 is equals to 0, A0 is coming back to 0. No, it's not true, because when A is equals to 0, the next state should be always 1. So next state should be always, it should going to be 1. For B, again it is coming back to 0 when A is equals to 0. Next one, if we see C, now at Q is equals to 0, yes, it is good that A is equals to, when A equal to 0, it is coming to the next Q, when it is coming to the Q is equals to 1 state, and when A is equals to 0, it is remaining at Q is equals to 1 state, and when A is equals to 1, it should toggle from 0 to 1 and 1 to 0. So option C is your correct option. Option D is also not correct because it is not toggling, so it is all wrong, right? The option C is your correct option. Great. Next question. The next question says that a traffic signal cycles from green to yellow, yellow to red, red to green. We know that how traffic signal work, right? In each cycle, green is turned on for 70 seconds, yellow is turned on for 5 seconds, and red is turned on for 75 seconds. Okay. The traffic light has to be implemented using a FSM, finite state machine. The only input to the FSM is clock of 5 period per second. 5-second period. Okay. So total time period by 5 seconds, right? Time period of 1. So now they are asking the total number of flip-flops required for the FSM. So how we find out total flip-flop they are asking. In order to find out the total flip-flop, we have to find out the total time. So how will be total time? So that will be total time divided by time of, or you can say time period. So total time will be equal to 70 plus 5 plus 75 divided by time period 5. So if you solve this, what will be 75 plus 75? 150, 150, that will be 30. So total number of flip-flop will be what? Is equals to log 30. So what will be the value of log 30 here? Log 30 will come out to be 4.91. So nearest integer to this, that will be 5. So 5 flip-flop will be required. Right. So how we calculated the number of flip-flops? So there is a traffic signal. So the total amount of time is there. So in order to shift from green to yellow, yellow to red, and red to green, we need 70 plus 5 plus 75 seconds. And for only one input of FSM clock is equals to 5 clocks. So how many number of unique inputs we will be needing? So this will be total number of unique inputs. So if I know the total number of inputs that will be required, so that is equals to 30. That we calculated by total time divided by the time period. So that we get out, got, that is equals to 30. So the total number of unique input we got. So number of flip-flop required in order to get this 30 amount of total unique inputs, that will be equal to log of 30. So log of 30 will come out to be 4.91, and the nearest option, the nearest value of flip-flop will be equal to 5, because flip-flop cannot be in decimal. Of course, they can be 1, 2, 3, 4 and 5 flip-flops. Next question. Okay, next question is saying the state diagram of a finite state machine FSM designed to detect an overlapping sequence of 3 bits is shown in the figure. So this is a FSM, the state machine diagram is given to us, and it is also an overlapping sequence as it is given. The FSM has an input in and output out. We know how FSM works. The initial state of FSM is S0. Now it's saying that if the sequence is this is the sequence given to this FSM, starting with leftmost bit, and the number of time out will be. So they are asking that how many times out will come out. So now first we have to see that what this FSM is repeating, that what is the overlapping sequence. So we can easily see from 0, 0 to 0, 1, it is shifting to next state when its value is 1. From 0, 1 to 1, 0, it is shifting when the value is 0. And from 1, 0 to 1, 1, it is shifting when the value is equals to 1. So what is the sequence it's detecting? Sequence detecting is 1, 0 and 1. Now we know the sequence. What we have to do is we have to see that how many times 101 is detected by the sequence, and the sequence is of course an overlapping sequence. So first we see here 101 number 1. Now since it's overlapping, it will also consider this. This is number 2. Again it will start, we can see number 3, and finally 101 number 4. So 4 times 4 times it will give us the signal out. First, we have to see that they have already given that the sequence is overlapping. We have to see that what sequence of finite state machine it is, right? So we just concluded that the sequence here detected by the FSMA is 101. Now they have given us the input sequence, right? And we have to find out how many times we are detecting 101, be it overlapping, right? So 1, 2, 3 and 4. 2 times it's overlapping, otherwise 3 and 4 are quietly visible so that they are not overlapping at all. Question. Next question. A finite state machine is implemented using D flip-flop. D flip-flop, that is A and B, and logic gates as shown in the figure below. 4 possible states of the FSM QA QB are 0, 0, 0, 1, 1, 0 and 1, 1. Okay. Now they are saying that assume that X1n is held at a constant logic level throughout the operation of the FSM. When the FSM is initialized with QA, QB, that is 0, 0, and clocked after a few clock cycle, it starts cycling through. Now, what they are asking is we have to find out at what possible values of XIN, that is your floating input, right? This is a floating input. At what possible value of XIN, we will be getting how many possible states. Now, we have to just draw the truth table for this. That's the only way that how to solve the digital circuits, especially when we are talking about some sequential circuits, right? So we have to always go with the truth table, right? Let's just start with, let's see first what is DA. So what is DA? This is a XOR gate. So DA is XORing QA and QB. That's it. QA XOR QB. And what is DB? DB is equals to QA X in bar, because this is a NAND gate. So QA X in bar. Now, if let's just say if X in is equals to 0. So if X in is equals to 0, DB will be equal to what? DB will be equal to, if not gate, if I am putting any one of the input to be 0, the output will be always 1. Because for NAND gate, we know the truth table for NAND gate, A, B and Y 0, 0. This is the output or truth table for NAND gate. If any of the input is 0, the output will be always 1. We should know that these small details, of course, right? So DB will be equal to 1 because X in is equals to 0, right? So now we can easily draw the truth table. So DA, so at X in is equals to 0, DA, DB and the next states Q n plus 1 Q, and this is Q of A n plus 1 Q of B n plus 1. Next, so inputs are 0, 0, or rather let me write like this. The initial states QA, QB and DA, DB. So DA, DB anyhow tells us the next state. DA, DB. 0, 0, 0, 1, 1, 0, 1, 1. Right. So for DB, it will be always equals to 1, no matter what other input is all about. Now for DA, we are XORing QA and QB. So Q 0, 0, 1 XOR 0, 0, 1, 1, 1 and finally 0. Now you see that how many states you are getting. Only this and this is occurring. So only 0, 1 and 1, 1 is occurring. So only 2 states are there. Only 2 states are there. So for x in equal to 0, here only two states for four possible states for x in is equals to 0. So that will be your correct option. So only two states are there when x in is equals to 0. So this is how we can easily calculate that how many states will be present by just simply drawing the truth table. So what we did, we just calculated the value of dA and dB by equation, and after that we put all the input states, that is equals to 0, 0, 0, 1, 1, 0 and 1, 1. So these will be the input value. After that we just calculated what will be the output values according to the equation, and we just found out that only two states will be there when xn is equals to 6. Moving on to the next question, the state transition diagram for a finite state machine. So machine states are given that A, B, C are the states. For the input x, y and z is equal to what? So what they are asking is the state ambiguity. So ambiguity basically means whenever the state is going to the other multiple states at a same time, right? When the state when the transition is occurring, when the output is occurring at multiple states at same time, like at same value of x, y and z, I am moving to state A and state C as well, both at same time, right? So that is ambiguity, ambiguous, right? So now in order to find out the ambiguity, what we have to do is we have to again draw the truth table, because in order, if we see the straight diagram, it will be very complicated for us to find out the ambiguity, that when the ambiguity is occurring. So we just draw the truth table. So take X, Y, Z inputs. For all the cases, we will be drawing this. Right. Now, for state A, if I am saying this is for state A, input and where the output is going. For state A, of course, the input will be always A only. And we have to now check the output, that if there is any ambiguity or not. Now, let's see. At x is equals to 0, y is equals to 0, output A, from A, it's going to B. We can easily see it's going to B. Now, for 0, 0, 1, for x is equals to 0, for y is equals to 0 and z is equals to 1. Now, y is not there. We can easily see for x is equals to 0 and z is equals to 1, the output is moving to itself. So, A, again for similar, for x is equals to 0 and z is equals to 1 in similar state, this will be again A. Now 0, 1, 0, when y is equals to 1. When y is equals to 1, in this case also it is going back to this state, right, itself, A. Now 1, 1, 1, 0, 0, 1, 0, 0 means when x is equals to 1 and y is equals to 0, so it's going to C. We can see that, right? For 1, 0, 1, that means when x is equals to 1, and it doesn't matter for the value of z, y is equals to 0. So y is equals to 0, x is going to C again. Clear it? C and C. Now for 1, 1. Now for y is equals to 1, it is coming back to A. And for 1, 1, 1. Now for y is equals to 1, x and y values don't care. So it is coming back to A. So this is having no ambiguity, right? In this case, there is no ambiguity. Now for state B, again, input for state B will be B only. We have to check for output for the ambiguity. Now, whenever y is equals to 1, it is coming back to itself. So whenever y is equals to 1, it is coming back to itself. So for this value, it will be b, b, b and b. Next, for y is equals to 0 and z is equals to 0, it is going to a. For this value, it is going to a. For this value, it is going to a. Now, for y is equals to 0 and z is equals to 1, it is going to c. For y equal to 0 and z is equals to 1, it is going to c. Y 0, Z 1, it is going to C. So again, there is no ambiguity in B as well. Let's see C finally. State C. So for state C, input will be C. We have to just check for the output, right? Just a minute. For C, right? For Z is equals to 0, we can directly see that for Z is equals to 0, it is coming back to C, right? So for Z is equals to 0, we can directly put for the here Z is equals to 0, Z is equals to 0, Z is equals to 0 and Z is equals to 0. So alternate. So it is coming back to C, right? Lastly, output I'll write here. So now next, for X is equals to 1 and Z is equals to 1, it is coming to A, but it is for X is equals to 1 and Z is equals to 1, it is for X is equals to 1 here and Z is equals to 1, it is coming to A. So A and X is equals to 1 here, also A, and last will also be A. But here also, if you see, for Y is equals to 1 and Z is equals to 1, we can see ambiguity here only, right? You can see that for Z is equals to 1, it is going to A, and for Z is equals to 1, it is going to C. So here the ambiguity will occur at this state. Now from C at Z is equals to 1, it is going to A and as well as it is going to B. So this cannot be possible. You cannot go to the different stages at same value of input. If you are given same input, you have to just move to one stage. You cannot go to two different stages at a time. So ambiguity will be occurring at C. So at this particular point, the ambiguity will occur. Okay, next. The digital logic shown in the figure satisfies the given state diagram. So digital logic will satisfy the state diagram when Q1 is connected to input QA. Now they are saying that it will satisfy this diagram when this is connected. That means when D2 is equals to this is XOR. Okay. Suppose that XOR gate is replaced with XNOR gate. Which one of the following option will preserve the state of the diagram? So they are saying that you have to preserve this. This should not be changed, but XOR gate is changed to XNOR gate. We have to find out this, that what changes will be occur when which value we have to connect with A, that is Q2 bar, Q2 or whatever, right? We have to find out. Now if I am converting XOR to XNOR, then very important property, we can say that if I have to convert XOR to XNOR, what can I do? I can either put A bar XNOR B, that will give me what? A XNOR B. If I am putting any one at bar, like if I have A XOR B, and if I put either A or B at bar, So what I'll get? X NOR as the gate. X NOR output I will get. See, this is how we convert it. So now what they are saying that instead of XOR, we have to use XNOR gate, right? So what I can do is I can take QN bar. So for QN bar, if I take, that will be the next output, the output of D1, that is Q1 bar. So I can connect this to A if my gate is replaced by this in order to maintain the state. Very easy. So what they were saying that, initially it was Q1 was connected to A. So initially Q1 was connected to A and the gate they were using XOR. So we know that D2 will be equal to A XOR S, and here A value is nothing but Q1 XOR S. So what I have to do is I have to maintain this. D2 here should be same as D2 previously, but I have replaced the gate from XOR to XNOR. So from this identity of conversion from XOR to XNOR, I can say that if I take Q1 bar and take XNOR as a gate, so I can get same value of dt as we were getting before when the gate were not interchanged. Okay, so what option will be correct? Input A should be connected to Q1. Input A should be connected to Q1, that's Q1 bar, that's it. There is no need to change anything else. Okay, the pointer P in the following figure is stuck at 1. What will be the output F? So that's an easy gate question. Now what is this? This is a large given and they are saying that it is stuck at 1. So P value is 1. So what is the value of this? So this is the NAND gate and this is what? This is B and this is both input shorted NAND. So this will be just C bar. So this is B, C bar, whole bar. Now output of this is given to this NOT. So this will be B, C bar, whole bar, whole bar. So that will be just nothing but B, C bar. And this is 1. So 1 NOT will be equal to 0. If I get 0 input at any, like if I get input 0 of NAND, this is NAND gate. If I am getting any of the input as a 0, so what will be the output? It will be always 1. So what I was saying that if any of the input of the NAND is equals to 0 at any moment of time, the output will be equal to 1, right? We know that how NAND works. So output will be equal to 1. It doesn't matter what value this is. So A into 1 NAND. So if we multiply anything with 1 with NAND, whatever value of other input we will get as it is, because C NAND A B Y. I am drawing NAND again in this class. So now if I am saying that one value is there, so whatever the other value, that will be reflected at the output. So we will get A. Now finally it will be A bar, because what we are getting, if we are having 1 here, so I am getting opposite 0 to 1, here also 1, 0 to 1, here also 1, 1 to 0. So whatever 1, if I have 1 as input of NAND, so output will be A bar, or easily can see from here as well. So it will be A into 1 bar, so that will be just A bar, that's it. So A bar, and finally the output, this is nothing but not A. So that will be your final answer. So that was all, right? So that was all about your digital circuits, and that was the last topic of the class. Thank you.